Okay. So the next theorem is about unique representation of vector relative to a basis. So suppose we have a basis. We select a basis B of a vector space B. Now, every vector, little v in capital V has a unique representation as a linear combination of distinct vectors in this basis here. So there is a closely related theorem we studied in section 2.4 in chapter 2 before. So let me say that. So we have shown in theorem 2.4.6. So you can review the theorem right now. Right? So the theorem states that so that each vector in the span of a linearly independent set. Linearly independent subset of a vector space. Has a unique representation as a linear combination of vectors in that set. Okay, so we compare the statement here and there. So it says that each vector in the span of a linear independent subset of vector space. So in the span of a linearly independent subset of a vector space has a unique representation as a linear combination of vectors in that subset. Okay, so now that subset will be a basis. Okay, so now since the basis we consider spans the vector space V, right? So every vector V in the vector space V is in the span of the V. Okay? So here, the span of a linearly independent subset. So this linearly independent subset actually is the basis. And the span is SPAN of the basis. And because B is the basis, so the span is V. Okay? So each vector in capital V is the same as each vector in the span of a linearly independent subset. And also, for basic span V and the sinks V is a linearly independent set. Subset of V, right? So B span the vector space V and the B is a linearly independent subset. Okay, so B is linearly independent subset and span the vector space. So the description in theorem 2.4.6 perfectly fits to a basis. So that any basis for this they have the okay. So that so every vector. So the conclusion is so obvious. So every vector in the capital V is a unique representation as a linear combination of distinct vectors in V. I forgot to put distinct. Sorry. So basically, this theorem 5.2.2 is the same as theorem 2.4.6. Okay. We just call such a set as a basis in chapter 5. Okay. So we call a basis is a linear independent subset, and this subset span the whole vector space. So that. Question? Okay. So now we consider a vector space V, okay, which has finite ordered basis. It could be U1, U2 up to UN. Right, so we order the vectors in B by U1, U2, etc. UN. So it's called ordered basis. And it's a finite set. Okay, we have only finite vectors in B. Alright, then each vector V in capital V can be expressed, right, as a unique linear combination of U1 up to UN. So V is written as C1, U1 plus C2, U2 plus plus Cn. Alright, so from the previous theorem, so when we have a basis which consists of finitely many vectors, then and we order all the vectors in the basis by integers, right? 1, 2, 3, 4 up to n. So that each vector in the vector space can be expressed uniquely, all right, as a linear combination in this form. So now the vector the column vector we use this notation. Going to be C1, C2 up to Cn. Or sometimes we use parentheses. Okay. So the column vector V, C1, C2 up to Cn in Rn, in an n-dimensional Euclidean space, is called the coordinate vector. The coordinate vector, right, of V associated with the ordered basis. Alright, so see here, we use B as the subscript here. So, it's a column vector. Right? Even though vector V can be very general, but for example, it's a vector space of functions or vector space of polynomials. Right? But once we have a finite basis V, like this one, we can construct a column vector here, right? By using the coefficients in the unique linear combination of V for the vector V. So we call them as the coordinate vector. Okay? Coordinate vector of V. All right, so now we characterize this process, okay? And so to summarize it into 5.2.3 plus 4. So I combine two theorems in textbook into this theorem here. So let B is a finite ordered basis. Right? Alright, so this B there. Then the function okay, so I use this notation, bracket with B as the subscript. So then the function for every vector in the vector space, we assign a column vector in Rn for it. Means that we assign the coordinate vector of V for this vector V. The assignment here, okay, it's bijective linear transformation. Okay, so it is a linear transformation from vector space V to vector space Rn first. Second is that it is bijective, means that it is 1 to 1 and 1 to. Okay, so first of all, I would like to show that it's a linear transformation. Alright, so relate to x, y, b in the vector space. Alright, so then, right, x is a unique representation as a linear combination of the basis vectors u1, u2, un, right? So the coefficients c1, c2 up to cn and y can be written as d1, d1, d2, u2 plus da plus dn, dn. Right, so then we have, so which are unique respectively. Okay. So the coefficients C1, C2, Cn are unique from our previous theorem. Right? So that okay. But I think at the moment I use T. For the name of the linear transformation. It's more convenient. And later on, I will call this T as the notation I want. Okay. Anyway, so for the moment I call it T. All right. And so, all right. So we have the T of x. It's which is C1, C2 up to Cn. Okay, and okay, fine. And the Ty, it's y, which is D1, D2 up to Dn. Okay. But now x plus y, right? So we add these two vectors together. So we have c1 plus d1, u1 plus cn plus dn, un. So that the coordinate vector of x plus y becomes to c1 plus d1, c2 plus d2, cn plus dn. Alright, so we just write down the coefficients here. And but this common vector can be written as the sum of two common vectors. And from here, we know this is just dx plus d1. Alright? So we find that this mapping, this function t, has this property that the function value of the sum of two vectors is equal to the sum of the function values. This was for here the sum. Also, for any scalar alpha, right? We have alpha x equal to alpha c1 u1 plus alpha cn un. Okay, so when we multiply a scalar alpha here, right, on both sides, then we have this one. So that T alpha x, alright, but the definition is alpha c1, c2 up to alpha cn. But what is that? This is alpha times c1, c2 up to cn. So this is alpha t x. Alright, so t of alpha x equal to alpha times t x. So from this one and this one, we have P is a linear transformation. So the conclusion is that. Okay? From V to Rn. By theorem, let me see. We have proved that in chapter 2, so the theorem is 2.4.6. Okay, so that we proved that 2.4.6. Okay, so we proved it's a linear transformation. So now we have to prove it is bijective. Okay, now to show that T is untrue, so here, for each column vector, C1, C2 up to Cn, right? We construct a vector V to be C1 U1 plus C2 U2 plus Cn U1. Okay, so we can construct that. So this vector, of course, is a linear combination of the basis vectors. And so this must be in V, of course. Alright, so let me say which must be in the vector space V. So by this construction, then we have, Tx, Tv, okay, is equal to C1, C2 up to Cn. Okay? So we construct a vector little v in capital V such that the function value is equal to this column vector. So this is true for any column vector in Rn. Okay? So this is V. Right. Okay, and so this shows that T is untrue. Alright. To show that T is 1 to 1, we just show the kernel of T is trivial. Alright, so we let X be in the kernel of T, i.e. T of X equal to 0. Okay? X equal to 0. And 0, just 0, 0, 0. So that is the coordinate vector of X associated with the basis. So then, by definition, then x is equal to 0, u1 times 0, u2 plus 0, u1. This is of course the 0 vector. Okay? So when the coordinate vector of x is the 0 vector in the Rn, then by definition x is just a linear combination of u1, u2, of u1 with 0 coefficients. So that x equal to 0. So any vector in the kernel of T is equal to 0. So that means that kernel of T consists of the 0 vectors only. So T is 1 to 1. Alright? Because we have shown that before. Okay. So T is 1 to 1. Oh, I checked for the theorem developed before. I come from okay, so I think that, all right, maybe I have to prove that. To be shown later. All right, sorry about that. It seems like I haven't proved that such a lemma before, so I will do that immediately. So anyway, so T is onto and 1 to 1. So that's T is bijective. Bijective for linear transformation. Just bijective. Okay. All right. So with that. All right. So I think I have to prove a theorem. So let the T be a linear transformation. Okay, from a vector space lead to another vector space. W. Alright, so the T. Now then T is 1 to 1 if and only if kernel of T is a trivial subspace. We do have such a theorem when we are considering linear transformation from Euclidean space to another Euclidean space. Okay, in that situation, in chapter 2 we considered that before, and we have that theorem when V and the W are Euclidean spaces. But the same result can be extended to linear transformation from arbitrary vector space to arbitrary vector space. Okay, approved. Reduction 1 to 1. Okay, so it's clear that T 0 go to 0. Right? We have that. So 0 goes to 0, cool. Because t is linear. But if you forget it, then I will show it. So this is the 0 vector in V, right? And t can be written as 0, 0, V, if you like. Alright, you multiply with 0. By linearity, this is 0, t, 0, V here. And 0 times any vector would be the 0 vector of W. Alright? So of course that clear. 0 vector will go to 0 vector. Right? By any linear transformation. So that 0 vector is in the kernel of T. So what is kernel of T? By our definition, we know this is all the vector in V such that T V equal to the 0 vector W. Right? This is the definition. And we mentioned that this is just the inverse mapping of this set, right? This is the inverse mapping for that. Okay, so we already know the 0 vector is in the kernel, of course. Now, if x is in the kernel of T, then we have Tx equal to the ZW. Right, we have that. But we also know that T0V is equal to the 0W, right? Okay, this fact we know that. Now, so this implies that x must be equal to 0V. Since t is 1 to 1. 1 to 1 means that if the function value are the same, then the vector in the domain will be the same. Okay, this is definition of 1 to 1. Right? So any vector in the kernel of T is equal to the 0 vector. So that it's clear that this is 0V. Okay? Alright, so we prove the forward direction. So when T is 1 to 1, then the kernel of T consists only 0 vector. Maybe I write it much more easy. Okay. Alright, so now we now prove the backward direction. The kernel here. Alright. Now assume that Tx equal to Ty. Alright? So we assume for x, y, v such that they have the same function value. Okay? Yes. To show that t is 1 to 1, we have to show that if this is true, then x must be equal to 1. Okay? Now by linearity, this is here. Or w, okay? So you by subtraction with that. And by linearity, this is so this implies that x minus y is in the kernel of T. But the kernel of T consists of only one vector. So this is implies as x minus y equal to the 0 vector. And this is implies that x is equal to 1. So T is 1 to 1. Right, so yeah. So you may refer to, so let me I make a remark. Please compare lemma 5.2.8 with theorem 2.3.1. Okay. So exactly, we have a version of the lemma in 2.3.1 in the section 2.3 in chapter 2. In that case, the V and the W are Euclidean spaces. So basically, we follow the similar approach for the proof. Questions? Okay, now before I developed our material, I would like to introduce a theorem, supplemental theorem, 1.2.8. Right, so a linear transformation P from V to W. Right, a linear transformation is bijective. Okay, it's bijective. If and only if it is invertible. Okay. In this case, all right, its inverse P from W to B is also a linear transformation. Okay. I think the first part is not strange, because we have shown that before, but in the context of function, the proof is here. A linear transformation. A linear transformation P from V to W is a function. So linear transform is a special type of function, right? So it's a function from V to W. Okay? So it's a function with some additional property, right? With linearity. So but anyway, a linear transformation is a function from V to W. And as a function, we prove that by theorem 2.3.8 in chapter 2, P is bijective. Alright, if and only if P is invertible. Okay? So we already know that. So we have an inverse function. Right? If a function is 1 to 1 and until then we will have an inverse function for that function. So that has been proved in chapter 2 in a supplemental theorem 2.8. Alright, so we let T inverse, right, from W to V be the inverse of T. Right, so the new part is to show that since T is linear, so the inverse is also linear. Okay, so that is the new part. Alright, so for W, the prime in the domain of the T inverse, right? So for two vectors, there exists unique, right? There exists unique is the mention mark. V and V prime in the here V such that T V equal to the W and the T V prime equal to the W prime. Okay, so we have that. And then T inverse of V is equal to V. T inverse of V, W prime is equal to the V prime. Right, so that situation, because T is bijection. Okay, so we have that. Alright, so there exists unique, the very important existence and uniqueness. Okay? Exists and unique. Now for scalars, alpha, beta, any scalars, T inverse alpha W plus beta, the prime. Okay, so we want to know that. Okay, and so that so this is the linear combination of W prime. T inverse alpha and W. W is TV, so it's TV beta, and the W prime is TV prime. Here, okay. Now T is linear because T is a linear transformation, right? So we apply the linearity. So T alpha V plus beta V prime. Okay, because T is linear. Things. All right. So T is linear. Now, and because T inverse is the inverse of T. So T inverse T, you have alpha V plus beta V prime. Okay? Because the composition of T and its inverse will be the identity. Okay? Or just maybe I will say identity of V of alpha V plus beta V prime. Okay? So the composition of T inverse since P inverse composition of P is the identity mapping of V. Okay? Maybe I do it step by step. This is identity. Okay? And identity, so that is alpha V plus beta V prime. But what is V? V is equal to the inverse of W. And the V prime is the inverse of the inverse of the prime. Okay, so you see that starting from here, the P inverse of a linear combination of W and W prime equal to the same linear combination with the same coefficient, right? And also the inverse of W and inverse of W prime. So, up to here, okay? So T inverse is linear. So, okay, so prove that it's linear. Any questions? Okay. So let me say it again. In this theorem, the essential part is that for any bijective linear transformation, its inverse is also a linear transformation, and it's also bijective, of course. Right, and then we also need another supplemental lemma. The composition is of P of two linear transformation P from V to W and S from W to U, right? So suppose we have two linear transformations, P from V to W, S is from W to U, then the composition, of course, is a function from V to U, of course. Of course, it's a function by composition. But since P and S are linear, so the composition, right, is also linear. Alright? So the proof. So the composition of two linear transformations is also a linear transformation. Alright, so the linearity is here. We check. Right? We check. Right? So we check a linear combination of two vectors in V. And we see, so that this is by definition of composition. Here. Okay? Now, because T is linear, so we have alpha T V plus beta T V prime. Since T is linear. Alright? So that this comes to a linear combination of PV and PV prime. And again, X is linear, so we have X of PV plus beta S of PV prime. Since S is linear. Okay? And now, by the definition of composition, okay? Alright, so now you can see that the composition of X and T is linear. So we're done. Okay, so let's take a short break up to 11 o'clock. Now, Now, so bijective linear transformation turns out to be an important class of linear transformation. So we will give a name for those bijective linear transformation. We call as an isomorphism. Okay? Right. So a bijective linear transformation from V to W is called an isomorphism from V to W. Okay. And in this case, there are two vector spaces. This we call we call that V is isomorphic to W. Okay, and we will list three basic properties of isomorphism. Denoted as V isomorphic to W. Okay? Right, so properties of isomorphism. Okay, one, reflexivity. Okay, reflexive. Alright? Reflexivity. Okay, I think that reflexivity is okay. Reflexivity. Alright, good. It says that any vector space V is isomorphic to itself, i.e. V isomorphic to itself. Right, so to prove that, let V is a function such that, so this is identity. So consider identity function V. Okay. So we consider identity function of V. And it is clear that the identity function ID V on V it's a bijective linear transformation from V to V. Okay? Identity, of course, is one-to-one armature, and it's linear, as we have long ago. All right, so now, with this bijective linear transform in the identity function, so with that, so that V is isomorphic. Because by our definition, if we have a bijective linear transformation from V to W, then we say that V is isomorphic to W. Okay? So V is isomorphic to V. Right. So the reflexivity can be established by using the identity function. The second is symmetry. If V, if a vector space V is isomorphic to another vector space W, then W is also isomorphic to V. Okay, it's called symmetry. The proof. Okay, so since V is isomorphic to W, there exists an isomorphism. There is an isomorphism P from V to W. Okay. Now, since P is a bijective linear transformation from V to W, okay, by theorem 5.2.8 and just proved its inverse P from W to V is also a bijective linear transformation. Alright, so we establish a bijective linear transformation from W to V. So we have W is isomorphic to V. So we have the result immediately from theorem 5.2.8. Okay. Alright, third property is about the transitivity. if a vector space V is isomorphic to a vector space W, and W is isomorphic to a vector space Z, then V is isomorphic to Z. Okay? i.e. V isomorphic to W and W isomorphic to Z implies that V is isomorphic to Z. Okay, it's called transitivity. So maybe I read it. Symmetry means that V isomorphic to W implies W isomorphic to V. Reflexivity means V isomorphic to itself. Transitivity means, I highlight them. Okay. Right, so you go through. Alright, so since V isomorphic to W and W is isomorphic to Z, there exists bijective linear transformations P from V to W and S from W to Z. Alright? So this is by definition of isomorphism. Right. So V is isomorphic to W because we can establish a bijective linear transformation T from V to W. And the W is isomorphic to Z means that we can establish a bijective linear transformation S from W to Z. Now, we consider the composition. Right? So, now consider S from V to Z. Right? Now, by lemma, by let me see. Okay, so by lemma 5.218, SOT is linear. Okay, we already showed that the composition of two linear transformations is linear. Also, since S and T, since T and S are bijective functions. Their composition is also bijective. So that is a bijective linear transformation. So that definition from V to Z, so that V is isomorphic to Z, i.e. V isomorphic to Z. Okay, so isomorphism has three properties. Okay, so that first, isomorphism is reflexive. Second, isomorphism is symmetric. Third, isomorphism is transitive. Okay, so we summarize into a theorem 5.2.5. Okay, so this is a theorem in the textbook. The relation of isomorphism among vector spaces is an equivalent. All right, so it's an equivalence relation. Because any relation which is reflexive, symmetric, and transitive will be called an equivalence relation. The statement here, given two bijective functions, their composition is also bijective. I assume you know this fact from high school, or at least in calculus. But if you don't know that fact, I think I have a direct proof for that. Okay, remark. So I give a remark here. Right? So remember, given T and X being bijective linear transformation. Alright? We have P inverse from W to V and the X inverse from Z to W. Right? Being bijective linear transformation. Okay, by theorem 5.2.8. Okay, because theorem 5.2.8 says that any bijective linear transformation is invertible, okay, and its inverse is also linear transformation. Okay? So P and X are bijective linear transformation, so their inverse are also bijective linear transformation. That is exactly theorem 5.2.8 says. Now we check the inverse on SP. Okay? Now we try to find an inverse to show that the position x of t is invertible. Right? So now we just directly saying that we just say, oh, its inverse is this one. But we have to check, right? So that this is so it's S. So this is ID. Right. So first of all, this one, and we also check ID W. So this is S. So this is okay. All right. So that means that T inverse composite S inverse is the inverse, because inverse exists in need of so now S composite with T is invertible. So by theorem again, by theorem 5.2.8, all right, it's a bijective linear transformation. Okay. So if you are reluctant to use this fact, maybe you forget it or anyway, right? Then you just apply theorem 5.2.8 again and again. Okay, so you can get the same result. All right, so I just what? Sorry, I forget the time because 11:20 is the time for you to take quiz. All right, so I finished here. All right, so okay.